Dear students, I am Suresh Halbandige from the Department of Physics, and I teach in Satish Pradhan Gyansapna College. Today, we will try to understand the phenomenon of interference of light. We are aware of the interference. When two or more light waves arrive at a point simultaneously, each wave has a displacement independent of the other, but the resultant displacement is the vector sum of the individual. As a result of which, when the two coherent light sources interfere with each other, we know that on the screen we observe alternate light and dark bands, and these light and dark bands observed are alternate and those are equidistant. The bright bands are equally bright and the dark bands are equally dark. So we'll try to understand the phenomenon of interference with physics simulation. Now in this case, we will take the two light sources, and from those we will get the interference. There is a concept called bandwidth. What is the bandwidth? The distance between the two successive bright or dark bands in the interference pattern is called as bandwidth. And we observe that the bandwidth is given by formula. I will write the formula here. Bandwidth X is equal to lambda into capital D divided by small. This is the formula for bandwidth. Now here X stands for the bandwidth, lambda stands for the wavelength of the light used, capital D is the distance between the source and the screen. Now here we observe that here this is the screen. Okay, this is the screen, and these two, okay, these two will act as the current source. So this is the one source, this is the another source. These are the two current sources. The distance between these two current sources is a small d. And this is your screen. And the distance between the source and the screen, this distance is denoted by capital. Okay, now here we observe the coherent sources are the sources of single wavelength, right? Now in this case, we shall take the two sources and I shall take the sources of light which are red in color. Wavelength is red color. Okay, so lambda stands for the wavelength of light. Now we start the animation, right? So here these are the two current sources. Now the waves are emitted by them. So this is emitting the waves. Okay. And this second source, this is also emitting the waves. Now the waves are emitted, right? And because of the interference on the screen, you observe, okay, on the screen, this is the bright band, this is the dark band, again this is the bright band. So dark, bright, dark, bright. In this way there are alternate bright and dark bands observed on the screen. Now here the bandwidth X is equal to lambda into capital D by small d. We can see the wonderful animation here. What is lambda? Lambda is the wavelength of light used. Capital D is the distance between the source. These are the sources and this is the screen. Small d, this is the distance between these two power sources. Now what I do is, here X is inversely proportional to small d. What I do is I'll stop the animation, okay, for the time being, and I will reduce the distance, right? Here okay, I have stopped the animation, right? Now here in this case, right, here I can reduce the distance. Okay, the distance between these two, I can reduce the distance in this way, right? A separation between these with the help of this cursor, I can increase or decrease. This is a small d, I am reducing it. I'll keep the distance between them minimum, right? So small d is minimum, so X bandwidth will be more. Okay, now I shall take the wavelength of the right as green wavelength and I'll start the animation. Let us see what happens. Okay. Now I will start this animation. Just a minute. Okay, I have started. So let us see the interference pattern on the screen. Right, we are able to see the perfect dark and bright bands. Now I'll change the wavelength. Just let us see what happens. I am moving towards the red color. You can observe the wonderful interference pattern on the screen. Now here the wavelength is increased. So bandwidth is increased. That's why we are able to see just one bright band and alternate dark bands. Now I will decrease the wavelength and move towards the orange color. Let us see what happens. Now see, we are able to see 3 bright bands and 2 dark bands. So here the wavelength is decreased, so bandwidth is also decreased. Still I will decrease the wavelength. Let us see what happens. So we are getting excellent alternate bright and dark bands. Now I will try to reduce the amplitude. Let us see what will happen. Intensity, we know intensity of light is directly proportional to the square of the amplitude. So amplitude is decreased, so intensity is also decreased. Now when I increase the amplitude, the intensity will increase and we can see the clear and distinct bright bands. Okay, now see, you are able to see distinct because I increase the amplitude. Because what is the relation between the intensity and amplitude? Intensity is directly proportional to square of the amplitude. So I have increased the amplitude. That's why I am able to see the clear, distinct, bright bands. So, dear students, so here what we have observed the interference pattern using double slit experiment. Okay, now we observe this phenomenon using the simulation is very easy to understand the concept of interference. I hope you might have liked this animation. If you like this, we can take many more such animations in physics. For today, we'll stop here. Thank you so much.